Okay, so let's start. Can you see my screen? Can you see forward and inverse kinematics? Perfect, excellent. And we have 62 people today. Good, great. Okay, so learning goals from today are the following. So we will see something called transformation hierarchy that will lead us to what is called forward kinematics and then to inverse kinematics. And this is related with your second coding assignment. I mean, I guess people is still doing the intro assignment, so maybe you haven't seen the oh, somebody saying that you cannot hear me. Give me a second. Okay, I think most people can hear me, so please write yes if you can hear me correctly. Yeah, so maybe it's on your side. And again, remember that I'm recording the sessions, right? So if anything is we have a problem on the session or whatever, yeah, you can see the session, the recorded session. Okay, good. So again, I was saying that this is very relevant for your second coding assignment. Basically, the actual assignment that we are asking is related with forward kinematics, and the bonus points is related with inverse kinematics. So I will show you a couple of hints today of how can you actually solve the bonus part from the coding assignment 2. Remember those this is the first assignment in which we have actual bonus points, and those bonus points are directly going to your final exam. So if someone managed to collect all the possible points from assignment from the second, yeah, for basically the following coding assignments plus the theory 4, you can get 20 points already for your final exam. So you'll have a more relaxed situation in your final exam. Okay, good. So last time we were talking about composition, transformation composition, right? And this is one of the examples that we were seeing, right? So when we want to apply different transformations to the same object, right? It could be like several rotations with translations, with scale, whatever. What we do is basically create different matrices and we just multiply those matrices, right? And again, please remember that we are always using the column vector notation. It means that matrices multiply the vector by the left side, and the order of operations is always from right to left. Okay, this is super important. Please never forget that. Okay, so now I will turn my camera. Give me a second. I need to stop share. So I guess you're seeing the dragon, right? Can you see the dragon? Backwards. Yes, I think yeah, we still have that problem. I don't know why. It's always reversed, but yeah, whatever. Okay. So what I want to show you today is my robot here. Okay. So I just bought this robot on Amazon. And yeah. So let's see how this robot behaves or how it moves, right? So I can control the robot from my keyboard. So I will tell the robot to stand up. Okay. So I have a button here to make it stand up. Okay. So now it's standing up. And what happened with the robot? If I tell the robot to move, I have another button here. Someone says Iron Giant fails. Yeah, kind of. Let's see how this robot moves. So if the torso moves, right, it basically gets like everything that is attached to the torso, right? If the upper arm moves, the other, right, the pieces that are attached to the robot are also moving, right? So there's like a hierarchy of movement on this robot. Do you agree? Right? So this is what we will see today. Uh, Imagine that again, that you are basically defining the transformation for something like this, for a robot, and each piece of this robot is basically or could be a different object, right? So if this is a 3D model, it could be a different object. And if you want to apply or to define the transformation of the hand, right? It will be incredibly complicated, or you will need to create like a very sophisticated sequence of transformations, right? So it will be better to kind of like inherit the movement from your parent object, right? So for the arms, for example, it is better to assume that their 0, 0 coordinates, or their world, is not the world but actually the torso, right? For the hand, for example, it's better for the hand to assume that its world is the what is the name of this thing? I think it's forearm, right? For each finger, for example, it's the same, right? For each finger, it will be easier for each finger to think, or to do the math, assuming that its world, its 0, 0, 0 coordinates is basically the hand, right? Instead of like trying to figure out everything. Okay, so let me just turn off my camera now, and I will come back to share my screen. Good. So can you see the presentation? It says transformation composition, and it's the same. Good, perfect. Okay, so let's keep going. So no robot anymore. Okay, so now let's see what happens with something like this. So imagine we have this system, right? So we have the bunny, and it's on top of a like a Greek column, okay? And basically we have two coordinate systems. We have the coordinate system A, which right now it's at 0, 0, 0, right? So the universe right now is the grid, right? And we have one coordinate frame, which is A, that is basically the coordinate frame, or the transformation matrix, or represents the transformation matrix of this column, okay? And again, it's in 0, 0, 0, it has no rotation. We have another coordinate frame that basically it represents the transformation from the bunny, and is the coordinate frame B, okay? And in this case, this bunny, or the coordinates of this coordinate frame is 0.45, 4.2, 0. Okay, so these are basically the coordinates of B with respect to the origin, which is basically the origin of the grid, right? This corner here. Or, I mean, we will see that we can also see it as the coordinates with respect to A, right? Because in the end, the bunny is on top of the column, right? Okay. So what happens if someone is just walking and it suddenly our bunny is almost falling, right? So now the transformation matrix from the object A, or the transformation A, is basically rotated 30 degrees, right? It's exactly at the same position, right? It's still in 0, 0, 0, but it's now rotated 30 degrees. And now the transformation matrix from the bunny is rotated 60 degrees, but 60 degrees with respect to A, right? Because if I compute, or if I see this rotation, the rotation of the bunny with respect to the world, can you tell me what is the actual rotation with respect to the world? Can you tell me how many degrees? 90, exactly. But I'm not writing 90 because, again, we need to see this as a hierarchy. So the bunny belongs to the column, right? It means that with respect to the column, it has only 60 degrees rotation, right? Good. So let's see what do we need to do if we need to get basically everything back, right? So what type of transformation do we need for or which transformation do we need to apply to the object A and the object B to basically get everything back? What do you think? What do you think about the transformation for A? So Nami is saying that the object A needs to rotate, right? It needs to have a positive rotation of 30 degrees, which is correct. CCW means contraclockwise, and if we are using right-hand notation, in general, in computer graphics, we almost almost use we almost use right hand notation every time. So basically right hand notation means that positive rotations are in counterclockwise, right? So a positive 30 degrees for A, right? And 60 degrees with respect to B, right? Yeah, it is correct. So let's see. So for the transformation matrix for A will be something like this. I'm not writing the entire matrix. So if I am writing this, rod Z 35 degrees, it means that we need to imagine that we have here an affine matrix, right? Which has a Z rotation with 35 degrees, right? Just to make it more compact and not having enormous matrices here, right? So everybody agrees that by just rotating 30 degrees, positive rotation by 30 degrees, the pedestal will be here, the column. Oh, sorry. Yes, thank you. It's actually 30. Yeah, this is my mistake. It's a typo. I wrote 35 here, but it's a typo. Don't worry. Yeah, it should be 30. Thank you so much. And again, don't worry, I will fix that on the video. I can edit the video. So yeah, we need to rotate this guy by 30 degrees, right? Good. What happens with B? Can someone guess how would the matrix of B look like? What do you think? Oh, someone is asking why Z? Well, because remember that I'm usually, if I am showing pictures in 2D, I usually tell you that I'm always assuming that it's 3D, right? So if you can see, we have a blue dot here. This blue is basically the Z axis, right? So we are seeing a 3D Euclidean world, right? And all these coordinate frames have X, Y, and Z. So right now the rotation is Z, right? Because the Z axis is the one that is basically not being modified. Okay. Okay, so Nami is saying, with respect to the world, rotation 30 rotation, then offset, then 60 rotation, offset. Yes, exactly. So the thing is, we already saw from the previous example. Remember that Wednesday, we were saying what happens if we want to rotate the bunny with respect to a point, right? So we were saying, okay, we need to transfer the bunny, right? We need to translate the bunny from that point to the origin, then apply the rotation, and then take the bunny back to that point, right? Here's something similar. In some sense, it's like this point here, the origin of this coordinate frame, is like the point P from that other question from Wednesday, right? But instead, what we will do now is basically compute the matrix as a hierarchy. So this is what we do. The matrix from the bunny will be basically to rotate 60 degrees. So remember, the order is always from right to left. Okay, so we need to read it from right to left. So rotation 60 degrees means that originally, or at the beginning, the bunny is like here, right? Because remember, originally this bunny is if it's an OBJ, it has its own coordinate frame, right? So its own coordinate frame, it has its own origin, right? Do you agree? So at the beginning, the bunny is not here. We need to imagine that the bunny is actually here. So the bunny first rotates 60 degrees, right? So imagine the bunny is rotating those 60 degrees. Then the bunny needs to translate this amount, right? Because this is actually the coordinates of this bunny with respect to the column, right? These are the coordinates. And then we just multiply everything, right, by the transformation matrix from the object A. In this case, from its parent object, right? So what happens here is, instead of trying to figure out for this bunny in particular, instead of having to figure out a more sophisticated sequence of transformations, right? We only care of its transformation with respect to its parent, and then we just get the transformation from its parent and just multiply it. Okay? Is that clear? Why do we multiply with A? Again, because A is the transformation from its parent. I will show you another example. Okay, so let's continue. Well, I have a quick break here for questions. So do you have questions from here? You want to raise your hand? David is asking what do okay those numbers, what those numbers mean. These numbers are basically the coordinates of this bunny with respect to the to its parent, right? So if I come back to this slide here, right? The column or the pedestal is basically the parent of the bunny, right? So this column here has its own coordinate frame here. So A is the coordinate frame from the column. So with respect to this coordinate frame, the position of B has these coordinates, right? But again, does someone wants to raise your hand and use audio? Remember that sometimes it's way more difficult to catch everything on the chat, right? Okay, David, so you are raising your hand. Unmute. Yeah.
Yes. Can you go to the next slide, please?
Yes.
Where the yes. Okay. So first question is this like a rotating clockwise? Why is it? Are you saying it's counterclockwise?
Oh, okay. Good question. What happened here? I mean, if someone was walking here and almost tripping with the bunny, yes, the rotation that happened here is clockwise, but the rotation we want to fix the problem is counterclockwise, right?
Oh, okay.
Yes. So because I'm asking, what do we need to do to get from this position to the original position? We need to get positive rotations. Yeah, maybe. Sorry, I think maybe my drawing is not very clear. It seems that I'm asking, what do we need to get from this position to this position? But no, it's like from falling to yeah. We want to get back to the original position. Thank you so much. It was a good question. Yeah.
Also, I have another question. Can you go to the next slide, please? Where A and B are filled. Yes. So yeah. So we hear A is it's like rotated 30 degrees, right? But the bunny is not rotated. Why do we just assume like we just do the translate afterwards?
Sorry, I didn't understand. Why you were saying that
Okay,
the bunny is not rotated?
So the bunny is
rotated.
rotated. The bunny is rotated like 90 degrees to the world.
To the world, but 60 degrees with respect to its parent.
But it's 60 degrees.
Yes.
Yeah, but we only did 30 degrees in A.
Yes.
Right.
Yeah.
So where's the 60 degree? That's like we have to do.
Well, these are the 60 degrees. Can you see my mouse?
Yes.
These are the 60 degrees that is the rotation from the bunny with respect to its parent, right? So we need to get first to get the bunny back those 60 degrees. But again, the bunny is not here, right? The bunny is on the origin.
So it's not written in there? So it's not written beside B? Because in B you just said A times the transformation. I mean translation.
No, but rotation is here. Here we have the rotation, 60 degrees rotation. The first.
Where's the rotation?
Can you see my mouse?
Yes.
Here it says it's rod set 60 degrees.
I don't see it. Oh, okay. Oh, it's blocked by the zoom. Oh, okay.
Oh, okay. Something was blocking your. Okay.
Yeah. The zoom box.
Okay, no worries.
Okay, sorry.
Yes. So this is, and again, you need to read everything from right to left, right? So this is the first thing that happens. Is this, the 60 rotation, the 60 positive rotation from the bunny. Then it's the translation from the bunny with respect to its parent, right? And then you basically multiply everything by your parent, right? Whatever you have in your parent.
Yes, that's clear. Because I didn't see the 60. I was wondering like where's the 60 part. Thank you.
Okay, good. So now, Nam.
Hello. Just to be clear, so if we actually wanted to just rotate the bunny 90 degrees instead, you would have to go through the 3 stages of transformation as we talked about before. You have to compute the offset and then rotate and then undo the offset. But here we don't undo the offset for some reason. So why is that?
Okay, so let's see. What you're asking is what happens if there's no column, right?
Kind of, but I guess this is the kind of the difference between for kinematics and just rotating with respect to the origin. But I'm confused as to why there's no undoing of the offset when you're computing B.
Yeah, it's a good question. The thing is, because now remember now the bunny, it's the parent of the bunny is not the world, right? Now the parent of the bunny is the column, right? So by multiplying by the parents frame, you're basically getting the advantage of moving the entire bunny with the column. So yeah, so let's see what do we need to do if there was no column, right? So let's pretend that there's no column, and we just have this bunny here, right? And we want to get the bunny from here to here. Let's pretend that. So what do we need to do? If we have an origin, there's no column, there's no hierarchy, and then we just have this bunny. If the bunny has this position right here, right, we would need to first get the bunny to the origin. Do you agree?
Yep.
Then rotate the bunny 90 degrees, right? And then get the bunny into this position. So we'll get to translate to the origin, rotate 90 degrees, and then translate to this position here, right?
Mm-hmm.
Right? But that is not necessary, right? It's not necessary anymore because you only need to apply its local rotation with respect to its parent, which is only the 60 degrees. Its local position with respect to its parent, right? Which is this amount. And the beauty also is that it doesn't matter now the new position from the bunny, right? So the bunny was originally here with my mouse is. Now the new position of the bunny is here, but its local coordinates are not changing, right? It doesn't matter if I keep rotating the column, the local coordinates of B are exactly the same. It's exactly the same number, right? Because it's with respect to its parent, right? So you're basically taking everything with the column.
So each joint is its own local coordinate origin, and there's no offset between the the root and the origin.
Yes.
Yeah. Okay.
Yeah. And again, that is probably the easy way to see it is like that. It's like for every object that has a parent, that object does not belong to the world anymore. It's okay. This guy now belongs to its parent, right? So everything that happens to that object, now it's local, right? That's why the rotation is not 90 degrees. It's just 60 because it's 60. It's like a local rotation with respect to its parent, right? Okay, good. So nobody else is raising hands, so I will continue. Okay, so we have the robot here again, right? So imagine that we have this robot, and obviously the robot has a lot of pieces, right? But let's just pretend that we have only 3 pieces that we care. Basically the torso, which has a first matrix or transformation matrix, which is M1, right? So let's say that M1 is basically the transformation from the torso. And again, it could be in any position, right? If the torso could be attached to the hip, right? For example, and maybe the hip could be the parent of the hip, could be the world, right? But for now, let's pretend that the parent for now is the torso, right? So this section here, right? This part of the robot, right? It needs a transformation matrix, right? So this guy here has some rotation and some translation with respect to its torso, right? With respect to its parent, right? So what does M2 look like? What do you think? Yeah, and Pavel says, nice, it saves a lot of going back to origin and coming back. Exactly. That is basically what we have here, right? It's way more convenient. Okay, so M2 is something like this. M2 will be some matrix, and by some matrix, what I mean here is some matrix is just its local transformation with respect to its parent, right? Because this guy could be like rotating, right? Or I mean, in this case, obviously the pieces of the robot are attached, so they cannot move per se. So it's only rotations, right? So this some matrix is its local rotation times the matrix from its parent, right? Kai is asking, why is some matrix on the right of M1? What do you mean? Oh, again, by some matrix, I mean that this is basically your transformation matrix, your local transformation matrix of this thing here, right? So you can rotate this arm or do whatever you want to this arm. That will be your this sum matrix. Yeah, sorry, maybe I need to use a different name for this, but maybe we can say some local matrix, right? So you have some local matrix with respect to your parent, and then you just multiply by your parent's matrix, right? So what happens with M3? What do you think it looks for M3? And Pavel is saying M2 times some matrix. Yes, exactly. So when you're here, you don't care anymore what is where is on the other chain, right? So way behind your chain. So now your parent is M2, right? So for M3, the matrix M3 is whatever rotation it has this piece times its parent, which is in this case is M2, right? So you don't need to like care about what is doing the torso or what is doing the hip or whatever. So this guy could be like dancing or whatever. It doesn't matter. It's for you is okay. I am locally, I don't know, rotating 45 degrees with respect to my parent, and that's it. It's just a 45 degrees rotation. That's it. I just multiply by my parent, right? So what about the hand? It's the same, right? Whatever local transformation you have for your hand times your parent's transformation, which is in this case M3, and you don't need to care, right, about anything behind that, right? Because everything is handled. Okay? With the robot example, it is clear now how this thing works. And again, in the end, this is the same topic, mathematically speaking, is the same topic than Wednesday, right? This is a composition of transformations, right? It's just the way we are encoding that information, the way it is, right? Each finger will be hand times some matrix. Yes, exactly that. Each finger, right? So this finger here, for example, where my mouse is, this guy, he doesn't need to care about the elbow or whatever, right? He's just saying, okay, my parent is the hand. So I only take the matrix of my parent and I multiply that times my own local transformation, right? So I am rotating 20 degrees. Perfect, great. Imagine how complicated it would be if you're doing a very complex animation and you need to figure out the transformation matrix of this finger without this concept of creating a hierarchy. Again, it is possible, right? Of course it is possible, but you need to decompose the entire rotation that you want in incredibly complicated going back and forth, right? It will be very, very, very confusing, right? Very difficult to do. But in this case, with this solution is obviously simpler, right? Okay. Good, perfect. Okay, so questions for now? Does anyone needs to raise your hand? If you have a question, please raise your hand. Okay, nobody's raising hand. Perfect. I'm yeah. Okay. I'm assuming that it is clear. Good. So now let's talk about the actual topic from today, which is called forward kinematics. What we've seen right now is actually that. It's called forward kinematics, right? So basically that is apply a sequence of transformations to a kinematic chain. So in this case, when you have several objects, right, with a certain hierarchy, right, that, at least in robotics, that is called a kinematic chain. In robotics and also in animation, right? In computer graphics, we call it animated chain, right? So imagine you have something like this, right? So we have two links. So this could be also similar to a robotic arm, right? And this is a kinematic link, right? And basically you have two links. Sorry, a kinematic chain, and this has two links, right? So usually each piece of your chain, it's called link, okay? And basically it's a hierarchy, right? So forward kinematics, again, is just apply a sequence of transformation to the kinematic chain, and at the end, you end into a final position. So what do I mean with this? So imagine here, for example, I apply a positive rotation to this object in particular. This is the parent of this guy, right? So for the first link, I apply some transformation, some rotation. Then I apply a local rotation. So can you see now this angle is with respect to its parent, right? So it's not with respect to the board, it's with respect to the parent. So this guy also has, in this case, a negative transformation, a negative rotation, right? And in the end, at the very end of your chain, you have a final position, right? So when you're doing forward kinematics, when you're moving the robot using forward kinematics, taking, applying the transformations first to the parent and then to every possible child for that chain, you end up, right? Your I don't know, maybe your index finger of your robot, right, ends into a specific position in 3D space. That final position, right? You're not controlling that final position, right? You're just applying rotations or transformations, and that final position is the resulting output from this sequence of transformations, right? So that is called forward kinematics, right? So in forward kinematics, you have as input, right? You have transformation data for each joint, right? Each joint or each link, right? And basically the output is the end effector position, right? So this final position, the name we usually call it in computer graphics or in robotics, is called the end effector. Okay, so the end effector is basically the last part of your kinematic chain. Okay, good. So what is inverse kinematics? So that is forward kinematics. What is inverse kinematics? It's exactly the opposite of that. So instead of having the transformations as input and getting it at the end, in the end, getting an end effector position, in inverse kinematics is the opposite. We have the end effector position and we need to compute the transformation data, right? So this is totally different problem, because now instead of just, okay, I will apply a rotation here and I apply a rotation here and I will see, oh, where am I, right? Now it's different. Now I need to tell the robot, right? Robot, please, I need you to touch this object here. I know the position of the end effector, and I need to, with only this position, I need to figure out which transformation needs to be applied for each link on my kinematic chain. Okay? So conceptually speaking, is this different clear for you? Again, conceptually speaking, is this clear? Say yes if it's clear. Good. Yeah, I think most people is saying yes. Good. So I will show you an example, okay? I will show you a quick example of this. Okay, so can you see trace to the max? Yes, yes, perfect. Okay, so this is forward kinematics, right? So this is a kinematic chain. There's a hierarchy here. If I get this object, for example, and I move this object, everything that is connected to the object is basically moving, right? So there is a hierarchy of transformations here, and this is a forward kinematic system, right? So if I apply transformation, in this case rotations, for example, to these objects, if I apply some rotation here, and some rotation here, right? And some rotation here, I end up with this position, right? I was not in control of this position in particular. I was applying some rotations, and then, right, the resulting effect by applying different rotations is that I could now see what is this position here, right? This is inverse kinematic. This is different. In inverse kinematic is backwards, right? I get the end effector, and if I move the end effector, right, the computer is basically solving, right, the actual rotation that I need for every single part of this kinematic chain, right? Yes, this is cool, right? Okay, Poe is asking, how is I key different from F key again? Okay, again, from FK, right, I have no control from the end position. So the end position is called the end effector. So it's basically this red position here, or red dot here. So what I do in forward kinematic is I just apply rotations to my robot, right? Where I apply transformations. In this case, it's just rotations, right? And then at the end, that sequence of rotations, right, gives you a specific position, right? But you didn't know that position from before. You were just applying rotations, and then, oh, yeah, okay, this is the place I got, right? After those positions, after those rotations. Inverse kinematic is the opposite. You take that position, or you define that position, and the computer it needs to solve basically your actual rotations, right? What do you need to do to get into that position in particular, right? So Tommy is saying, so basically one controls the end effector and the other doesn't. Yes, exactly. Yeah. It just, again, it's just the way, it's the difference between your input and your output, right? And in inverse kinematics, your input is the end effector. You are telling the robot, I want you to touch this point here, right? And you need to compute the necessary rotations for all your kinematic chains, right, to actually achieve that position, right? Is there a difference in performance for both? Well, obviously, it is more expensive to compute inverse kinematics than forward kinematics, right? Because, I mean, as you will see in my slides, it's not trivial, right? I mean, forward kinematics is trivial. It's just, you're just computing, and you're blind. You're completely blind of what is your end effector position is, right? You're just applying, for example, I don't know, if you want to make, what I mean is, if you want to make your robot dance, for example, right? You can just say, oh, I will rotate the arms of the robot by 30 degrees or whatever, but you don't care the position of the hands at the end, right? You're just like making the robot dance, right? It's just rotating. You don't care, right? But if you want to make the robot to write, that is different, right? Because if you want to make the robot to write or to draw something, you are defining the end position of your hand, right? So that is inverse kinematics. Okay, so let's see. That is the difference, conceptually speaking. So can I... and Nam is asking, does IK involve Jacobian transpose? Yes, it could. The thing is, inverse kinematics is very complicated, and in robotics is very sophisticated, because for robots you need to actually take into account the mass of the robot, right? I will show you who is Jacobian. I will show you the simplest version of inverse kinematic, which is useful for computer graphics. Okay, so let's see. So the simplest IK solution, the simplest way to see this problem, is basically as a geometric problem. Okay, so let's imagine that this is our kinematic chain. So this is link 1 and link 2. So imagine again that this is the robot's arm, or whatever, the finger or whatever, and this is the origin of your kinematic chain, right? And this is your end effector, right? Basically, you want to get with this kinematic chain, right? You need to get into this point. So what happens is that L1 can be represented by a circle, right? Basically the length of L1 is just the radius of a circle, and the length of L2 is just the radius of another circle, right? Whose center is now the end effector. If you find the intersection between those circles, is basically, in this case, is position 1, is P1, is basically the position in which you need to get, right, this kinematic chain, right? So you can then compute your angles, right? This is the simplest way to compute an inverse kinematic problem for only two links. Okay. So let's see here. So again, you have link 1, link 2. You have the position P, which is the end effector, right? So again, I'm showing you the arm of the robot with rotation already, right? But we don't know this rotation. So imagine that originally this robot, for example, is maybe like vertical, and you don't know how much you are rotating L1, and you don't know how much you need to rotate L2 to achieve this position, right? So the way you compute that is, the easiest way, again, is seeing this as the intersection between two circles, right? And one way to actually solve that problem is to compute this point J. So this point here, right, is the intersection between these two circles. You agree? Remember, L1 is a circle which has its origin here. So L1 represents one circle, right? And L2 represents another circle, right? And its origin is the end effector, right? So basically, the projection between this, in the intersection between those circles and this line here is this point J. If you can find this point J, then you can use just Pythagoras, very easy. You can use Pythagoras to find this position here, up here, right? So Paul is asking, the radius of the circle is the length of the arm. Yes, it's the length of the link, right? And yeah, the arm. If we usually call it links, but yeah, you can also call it arms, of course, right? Okay, and again, I'm showing you just a possible way to do this, right? So as I said, we are studying the inverse kinematic problem as the simplest way to study it is basically as the intersection between two circles. But in particular, instead of finding the intersection directly, I will try to find this position here, which is basically the projection. And you can use this theorem, okay, that says that the distance A divided by B is equal to C divided by D. This is it's a triangle theorem that is universal for any possible triangle. So let's see what are those distances. So A is basically the distance between the origin of your kinematic chain, right? The origin of your entire robotic arm and the end effector. Do you agree? This is this distance, right? Then we have S1, which is basically the intersection between this radius. Remember, L1 represents a circle, right? So it's basically the distance between O and S1 is basically this radius, right? It's basically L1, right? It's like intersection between this circle with this line. S2 is the intersection between the other circle with this line. And M is just the middle point between S1 and S2. Okay? So the distance C is the distance between S1 and S2, right? So I have C, right? I have A, right? I also have B, you agree? Because B is the distance from the origin to this middle point here, right? The only distance that I don't have originally is the distance D, right? This is a variable I need to compute, right? If I compute this distance, because I have everything except for, I have everything except for J, right? So I can compute this distance using this theorem, right? I can compute D with this theorem, and basically I get to this point, right? And again, so this is an example of this theorem. The theorem is valid for every possible triangle. So it's a very quick way to compute this point J, which is, again, this is just the projection of the intersection of these two circles with this line here. And this theorem is spooky math. It's not that spooky, it's just geometry. This by the way is my theorem. I published this theorem in 2014, but it's in a very in a very like low level conference actually. But okay, so this is one way to compute it, right? Again, you can compute it. You can compute the intersection between these two circles, with whatever other method you want. But this is probably the simplest. So now let's see what happens when instead of having only two links, right? So first, I guess it's easier, or it's easier right now to understand that computing the inverse kinematics for only two links is easy. It's just like intersecting two circles, right? That is basically what we are doing. But what happens if you have multiple links? That is a different thing, right? So in order to solve this, you need to use something that we call variable links, or variable length links. So I will show you an example of that. And I will obviously not have enough time to actually show you everything today. So because this is related with the extra points for your assignment, my plan is to actually create an extra video. But let me show you. Yeah, variable join. So this is what I mean when I said variable joins. So look at this kinematic chain. Can you see the trees to the max? Say yes if you can see it. Yes. So as you can see here, it seems that we still have a kinematic chain with only two links, right? The difference is that one of those links is like a telescopic link, right? That can vary its length, right? The way you compute this is using basically the same principle. You need to just compute the intersection between two circles. The only difference is that one of those circles, its radius is not oh, nice. Okay, so it's the radius of one of those links, right, is not fixed, right? So you can define how much that radius can like contract or extend depending on how far is the end effector. So in this animation, you can see that if the end effector is very close to the origin, right, this link here basically contracts, right, because it doesn't need to be like completely like in its entire length, right? If the end effector is very far, right, it's basically getting its entire length, right? So this is basically what we will do, or this is conceptually what we will use to actually solve a multiple link inverse kinematics. Okay, what happens is that you compute from the end effector to the origin of your kinematic chain. You compute everything as if you had variable or flexible links, right? And basically your solution for the first problem, inverse kinematic problems, becomes the end effector from the next one. And then you compute this, right? This inverse kinematic problem, and that solution becomes the end effector from the next one and from the next one, and basically you go backward, right? And with that, if you compute everything there, you end up, give me a second, you can do something like this. So I'm showing you here is, hopefully you can see it in a good speed. This is what you need to achieve to get the bonus points from the second transformation assignment, for the coding assignment. So Tommy is really? Yes, really. Basically, the first part of your transformation assignment is just using transformation hierarchies, and combine them in a forward kinematic approach, right? If you want to make the octopus to actually walk, right, you need to use inverse kinematics, right? Because then you need, in this case, you need to define a path for every leg, right? And you basically need to accomplish this by using inverse kinematics. But again, I need to finish for today, because we finished. I will make other video. I will make an extra video giving you a lot of hints of how exactly you could achieve the bonus points. So it's related with Bezier curves. We already talked about Bezier curves. Remember that I think in our first lecture we actually coded a Bezier curve. So it's related with Bezier curves. It's related with inverse kinematics. So yeah, I will show you that in an extra video. But yeah. So any question? We need to wrap up. Does someone wants to raise their hand? No? One last question? No? Okay, good. So I think we can finish. Oh, sorry. Nam is having a question. So this will be the last question. Yes, Nam, I can hear you.
Hi. So I see in the chat the math of the circle-circle intersection is not entirely intuitive. So just to check the concepts for sure. So IK is nothing but just an optimization problem where you solve for the transformation matrix given the untransformed coordinate and the transformed coordinate, right? And
Yes,
a circle-circle is just an instance of analytical solution for solving for that transformation matrix.
yes. But if it's a circle-circle, if you model the problem as a circle-circle intersection problem, is not an optimization anymore, right? It's just the simplest way in which you can geometrically compute this, right? Because this is computer graphics, but we don't care about efficiency. For example, in robotics, if you want to compute the inverse kinematics for robotics, you need to get into the most efficient sequence of transformations to get to the end effector, right? Because you don't want to lose energy in your rotors, right? But in this case, we don't care about that. So geometrically speaking, the easiest way to see it is just by intersecting two circles. And of course, it's probably not intuitive, because what I wanted in this lecture is just give you the concept, right? The conceptual idea, right? So I hope the conceptual idea is clear, right? On how or on what is the difference between forward kinematics and inverse kinematics, and that inverse kinematics, the way we can solve it, the super simplest easy way, is by just intersecting two circles. How you actually intersect those two circles, again, it could be with my theorem and this thing that I will explain in the extra video, or I mean, intersecting two circles, you can probably find that in any algebra or analytic geometric book or whatever, right? I mean, intersecting two circles is something from high school, so you can do whatever you want to compute the intersection between two circles. But yeah, but for today, it's just the conceptual idea. So I guess I hope
just one
that
more
is clear.
thing.
Yeah.
So given the same end effector position, there can be multiple configurations achieving the goal position. So does the circle-circle intersection take the multiple possible solutions into account?
Okay. Look at this. If your kinematic chain has only two links, right?
Mm-hmm.
There are only two possible solutions, because if you have two circles, right, two circles will intersect into points, right? So
Right.
if it's only two links, there are only two possible solutions, and those possible solutions are literally the intersection of those two circles. So there's no need of any optimization or anything like that. Usually in robotics, for example, you don't have only two links, you have more links. So if you have more links, of course, there are multiple solutions. Actually, if the end effector is achievable by the kinematic chain, and the distance between the origin of your kinematic chain and your end effector is less than the entire length of your chain, right? Because imagine that the end effector is exactly at the same distance of your entire length, right? The sum of the lengths of all your links. In the end, your kinematic chain will be completely straight, like a straight line, right? So that is also a single solution. So if that is not the case, if the end effector is closer to that, basically there are infinite possible solutions, right? Because the arms could have many different types of configurations. So that there is where there's a lot of research about that, and there is a lot of research in robotics to actually compute the most optimal solution. In computer graphics, sometimes you also want to compute the most maybe not necessarily the most efficient solution, but the most, for example, the solution that is closer to the way I don't know, humans walk, for example, or closer to the way animals walk. So in your group, for example, I don't know if you are literally getting into inverse kinematics, because I know that you usually use deep learning, right, to actually make characters walk. But yeah, but there are many possible constraints that you could have to actually decide which is your best solution. But what I will show you, because in the end, I mean, I cannot ask you a super crazy assignment, right? So for the assignments, we will not have crazy constraints. It's just a geometrical approach for the inverse kinematic problem. And so yeah, so we will not care about like any type of optimization or anything like that. We will just use circle intersections, variable length links, and that's it. Yeah.
Cool.
Good. Okay, so we need to finish because it's already 1 hour. See you guys. See you on Monday. Bye.